Thousands of years ago, humans looked at the night sky and believed that the stars were quiet, distant points of light. Nothing more, nothing less. For most of our history, we assumed our solar system was unique. We believed that the sun and its planets were a rare arrangement, perhaps even a cosmic exception. This belief lasted until the late 20th century, when our instruments became sensitive enough to notice extremely small movements in distant stars. Those movements were the first signs. When a star wobbles, even slightly, it suggests the presence of an unseen planet pulling on it with gravity. Gravity is simply the attraction between two objects with mass. A planet pulls on its star, the star pulls back, and the dance becomes measurable if our tools are precise enough. In 1992, astronomers detected the very first confirmed exoplanets, planets outside our solar system. They were orbiting a pulsar, the spinning remnant of a dead star. It was an unexpected place to find worlds, because the environment near a pulsar is extremely harsh. Radiation is intense. Temperatures shift violently. It is not a peaceful home for life. Yet those worlds existed. Their discovery opened a quiet doorway in our understanding. If planets could survive around a dead star, then planets might be everywhere. In 1995, a second discovery changed everything again. A planet orbiting a sun-like star. This planet, called 51 Pegasi b, was a hot Jupiter, a giant world orbiting extremely close to its star. Its year lasted only a few days. Its atmosphere was heated to extreme temperatures, and it challenged every idea we had about how planets should form and behave. The moment humanity realized that such planets were real, something subtle shifted. The universe suddenly felt larger, more diverse, and less predictable. For the first time, we understood that our solar system is not the normal pattern. It is simply one example among billions of possible arrangements. Some stars hold giant planets that skim their surfaces. Some hold small, rocky worlds in cold, distant orbits. Some hold nothing at all. As we gathered more data, more worlds appeared. First tens, then hundreds, then thousands. Each discovery carried a sense of wonder, but also a quiet discomfort. The more planets we found, the more we recognized how small and delicate our own world is. Earth is not the universal model. It is one configuration in a vast cosmic field of possibilities, many of which are violent, unstable, or completely alien. Astronomers sometimes describe this realization as a cosmic adjustment. It means accepting that the universe is not built for us. It simply exists, vast, indifferent, and full of worlds that do not match our expectations. Even today, when telescopes detect the faint dimming of a star caused by a planet passing in front of it, the feeling returns. It is the same quiet moment that the first astronomers felt decades ago. A soft, silent message carried across light years. There are other worlds, and they are nothing like home. This first step becomes the foundation. The discovery of exoplanets did not only reveal new worlds, it reshaped how we see our own and marked the beginning of a story that will follow us through every chapter ahead. When astronomers studied the first confirmed exoplanets, they expected to find worlds similar to the ones in our own solar system. They imagined rocky planets near their stars, gas giants farther away, and stable orbits shaped by calm gravitational balance. But the universe quickly revealed something very different. Some exoplanets orbit so close to their stars that their surfaces reach thousands of degrees. Their atmospheres swell and evaporate, forming long tails of gas that trail behind them like quiet cosmic comets. These planets should not survive such heat, yet they continue to circle their stars with steady rhythm. Others orbit in strange, stretched paths called eccentric orbits. Instead of following smooth circles, they travel in long ovals. This causes extreme seasons and violent temperature swings. A world may freeze in deep darkness, then swing inward toward blistering heat, all within a single year. There are planets with masses far heavier than Earth, yet they remain small and rocky instead of becoming gas giants. There are planets lighter than expected, puffed up like warm balloons. Some are covered in oceans of molten rock. Others are made mostly of water, forming global oceans hundreds of kilometers deep. These strange combinations challenge our understanding of how planets form. Traditional models say a planet's size, mass, and distance from its star should follow predictable patterns. But exoplanets break those patterns again and again. Their orbits can be unstable. Their temperatures can be extreme. Their atmospheres can rise and collapse. Astronomers sometimes describe these worlds as cosmic contradictions. They exist in places where planets should not form, or conditions where planets should not remain. Yet they endure, drifting through their unusual environments with quiet persistence. The more of these worlds we find, the clearer it becomes that our solar system is only one version of what a planetary system can be. The universe allows for combinations we never predicted, shaped by forces we are still learning to understand. These unexpected planets remind us that nature does not follow our rules. It follows its own. And as we continue this journey, we begin to realize that what we once considered impossible may simply be rare, fragile, or waiting to be discovered in the silent depths of the sky. As astronomers discovered more exoplanets, their early excitement slowly shifted into something quieter and more cautious. At first, each new world felt like a small celebration, proof that planets were common, and that the universe was filled with possibilities. But as the details emerged, the picture grew more complex. Many exoplanets looked nothing like the safe and stable environments needed for life. Some orbited so close to their stars that their atmospheres boiled away. Others drifted so far out that their surfaces were colder than deep space. A few had day-night cycles so extreme, but their landscapes were reshaped by constant melting and freezing. This diversity forced astronomers to reconsider their expectations. For decades, we imagined that most planetary systems would resemble our own. A warm zone, a few rocky planets, gas giants farther out, predictable orbits shaped by calm gravity. But the universe had different ideas. One turning point came when astronomers observed the first hot Jupiters. These giant planets orbited their stars in just a few days, skimming the stellar surface. Traditional models said this should be impossible. Giant planets were expected to form far away, where gas was abundant and temperatures were low. Yet there they were, drifting in blistering heat. Another shift came from planets with wildly unstable orbits. Some worlds move in tilted paths. Some orbit backward in the opposite direction of their star's rotation. These behaviors suggested that many planetary systems had violent pasts, collisions, gravitational battles, worlds pushed inward or flung outward. The more astronomers studied exoplanets, the more they realized that planetary systems are often shaped by chaos. What appears stable today may have survived countless disruptions, and what looks predictable on paper may behave unpredictably when examined closely. This growing understanding created a quiet sense of caution. The universe was not simply surprising. It was telling us that our assumptions were fragile. Astronomers began to approach each new discovery with balanced curiosity. They still felt wonder, but they looked for hidden dangers too. They asked whether a planet was stable, whether its star was calm, whether its orbit would last. They checked for signs of violent histories and unpredictable futures. The shift from excitement to caution was not fear, it was respect. Exoplanets showed us that the universe is broader and more intricate than we imagined. It reminded us that Earth's stability is not guaranteed elsewhere. It taught us to observe carefully, to question our expectations, and to recognize that the cosmic order we know is only one possible version among countless others. In this moment, astronomers learned something essential. Discovering new worlds is not only a journey outward, it is a quiet invitation to rethink how little we truly understand. When astronomers first found planets that looked similar to Earth, hope rose quietly in the scientific community. A world with the right size, a world at the right distance, a world with temperatures that suggested the possibility of liquid water. It felt like we were finally getting close to finding a true second Earth. But as data improved, these hopeful worlds revealed themselves to be far less familiar than they first appeared. Their surfaces were shaped by forces that Earth never experienced. Their atmospheres were unstable, or toxic, or too dense for life as we know it. The early promise faded into a more complicated truth. A planet can look Earth-like from light years away, but that appearance is often an illusion. Many of these so-called twins orbit stars that behave very differently from our Sun. Some stars release frequent flares, bursts of radiation strong enough to strip away atmospheres. Others are so dim that their planets must orbit extremely close, creating violent tidal forces. These forces can lock a planet's rotation, leaving one side in eternal day and the other in endless night. Even when a planet sits in the habitable zone, the region where temperatures could allow liquid water, the details matter. A slightly thicker atmosphere can trap too much heat. A thinner one can lose warmth too quickly. Small differences in composition, pressure, or cloud cover can turn a seemingly stable climate into one ruled by storms, frost, or boiling seas. As observations became more precise, astronomers began to see how delicate Earth's balance truly is. Our climate is moderated by the exact mixture of gases in our air. Our surface temperature is controlled by the distance from the sun, the tilt of our axis, and the presence of oceans. Remove or alter any one of these factors, and Earth would become unrecognizable. This realization led to a quiet shift in perspective. The universe may be full of Earth-sized planets, but very few behave like Earth. Size alone means little. Distance alone means little. Habitability is not a simple checklist. It is a fragile, and unlikely combination of countless conditions. These lessons softened the early excitement and replaced it with a more thoughtful curiosity. We still search for worlds that resemble our own, but we do so with the understanding that resemblance is only the beginning of the story. The illusion of a habitable twin reminds us that Earth is not easy to duplicate. Its stability has been shaped by billions of years of quiet adjustments, rare coincidences, and delicate balances. Each exoplanet we discover deepens that understanding. It shows us that familiar shapes can hide unfamiliar realities, and that the true nature of a world is often far different from the promise it first appears to hold. As our telescopes grew stronger, the number of known exoplanets rose faster than anyone expected. At first, each discovery felt like a distant miracle, a new world, a new possibility, a reminder that the universe was wide and full of potential. But as the count passed 1,000, then 2,000, then 5,000, a quieter realization emerged. There were not just a few planets that looked potentially habitable. There were many, and this abundance did not bring comfort. It brought questions. From far away, some of these planets seemed to sit in gentle orbits where temperatures might allow liquid water. Some were similar in size to Earth. Others circled calm, steady stars. On paper, they appeared promising, but the more we studied them, the more we saw cracks beneath the surface. A planet can orbit in the right zone and still be completely inhospitable. It can drown in thick carbon dioxide. It can freeze under reflective clouds. It can bake under a sky packed with methane. The habitable zone is not a guarantee. It is only a suggestion. As the number of candidates increased, scientists began to recognize a deeper truth. Habitability is rare, not because planets are rare, but because stability is rare. A world must hold its temperature within a narrow window for billions of years. Its star must shine steadily. Its atmosphere must remain balanced, neither collapsing nor expanding. Small differences over long timescales can turn an almost Earth into something very different. This understanding created a strange tension. We were finding many planets that looked hopeful, yet almost none that truly matched what life needs. The abundance of worlds emphasized how unique Earth might be. It forced astronomers to confront a possibility they had not expected. If so many planets can imitate habitability without achieving it, then true Earth-like conditions may be far more exceptional than we ever imagined. This thought brought a quiet, reflective discomfort. It was not fear, it was recognition. The recognition that our home is not easily replaced, and that the comfort of numbers can lead us to overlook the fragility of what we have. Finding many planets is not the same as finding many homes. And as the journey continues, this realization will follow us, shaping how we search, how we hope, and how we understand our place among the countless worlds of the cosmos. When astronomers first measured the atmospheres of distant exoplanets, they expected to find layers of gas somewhat like those on Earth, thin in some places, thicker in others, shaped by temperature, sunlight, and gravity. But the reality proved far more extreme. Some exoplanets possess atmospheres so dense and heavy that they defy intuition. These atmospheres are not gentle blankets of air. They are crushing shells of gas, thick enough to press down with immense force. On certain worlds, The pressure at the surface could flatten mountains, collapse metal, and destroy any form of life long before temperature or radiation ever became a problem. This happens because gravity and temperature work together in surprising ways. A planet with strong gravity pulls its gases tightly toward the surface, packing them into a dense layer. If the planet is also warm, those gases expand upward, creating deep, towering atmospheres that extend far into space. The combination creates an environment unlike anything on Earth. Venus provides a small example of what such conditions can become. Its atmosphere is about 90 times thicker than Earth's. But on some exoplanets, the pressure may be hundreds or even thousands of times stronger. A human would not simply struggle to breathe. They would be crushed instantly, long before heat or chemical toxicity could take effect. These atmospheres are often filled with complex mixtures of gases. Carbon dioxide, methane, sulfur compounds, and unknown chemicals blend into dense fog-like layers. Sunlight struggles to pass through. Winds move slowly under the immense weight. The sky may glow dimly, filtered through thick clouds that never fully lift. In some cases, the atmosphere becomes so deep that it blurs the line between air and ocean. Gas transitions into supercritical fluid, a state that is not quite liquid and not quite gas. It flows with the weight of water, but expands like vapor. This environment challenges the traditional categories of weather and climate. These crushing atmospheres remind astronomers that stability is not guaranteed across the universe. Some worlds grow calm, breathable skies. Others create heavy, suffocating shells shaped by gravity and heat. Each new discovery broadens the range of what a planet can be. By studying these dense atmospheres, scientists learn more about the delicate balance that keeps Earth's air at the perfect thickness for life. And they are reminded that even small changes in pressure, temperature, or composition can transform a world into something alien, harsh, and endlessly fascinating. As astronomers observed more exoplanets, they began to find worlds where the idea of an ocean took on a very different meaning. On Earth, oceans are calm in places and stormy in others, but always liquid, always bound by stable temperatures. On many distant worlds, oceans behave nothing like this. Some exoplanets orbit so close to their stars that their surfaces reach extreme heat. At these temperatures, water cannot remain liquid. Instead, it boils continuously, rising into the atmosphere as steam before condensing and falling again in violent cycles. The result is a world where the ocean is trapped in a loop of constant evaporation and rainfall. This cycle is driven by the intense radiation from the nearby star. Radiation in this context simply means energy released as light and heat. When a planet orbits too close, the star overwhelms the surface with energy, heating the water faster than it can cool. Waves turn into clouds, clouds turn into storms, and storms return to the sea with enormous force. Some planets may not have water at all, yet they experience similar processes. Instead of water, their surfaces may hold oceans of molten rock. These lava oceans behave like liquid stone, glowing with deep red light. They rise and fall as the planet rotates, reshaped by temperature and gravity. When the star heats one side, the molten surface churns like a slow, luminous tide. On other worlds, Superheated winds move across the surface at incredible speeds, carrying vapor, dust, or droplets of melted minerals. These winds are driven by temperature differences so extreme that air behaves more like a flowing fluid than a gentle breeze. Even planets that lie slightly farther from their stars can experience unstable oceans. If their atmospheres trap too much heat, a runaway greenhouse effect can occur. This is a process where heat builds faster than it can escape, causing the surface to warm endlessly. Over time, oceans turn into vast layers of steam, covering the planet with thick clouds that never lift. These environments teach astronomers the oceans are not simple features. They are fragile systems shaped by temperature, gravity, atmosphere, and radiation. Change one factor, and a calm sea becomes a violent storm belt. Change another, and water becomes vapor, or stone, or nothing at all. By studying these boiling or molten oceans, scientists gain a deeper understanding of how delicate Earth's conditions truly are. Our oceans remain liquid because our temperature is balanced. Our atmosphere protects but does not smother. Our star warms but does not scorch. These finely tuned conditions are far from common. Each extreme ocean discovered across the galaxy reveals another way a planet can evolve, survive, or transform. And each one reminds us that water, stability, and life are not universal. They are rare achievements in a cosmos filled with worlds shaped by relentless heat and endless storms. When astronomers began studying exoplanets in close orbits, they discovered a pattern that reshaped our understanding of how many planets experience time. These worlds often rotate so slowly and orbit their stars so tightly that one side of the planet always faces the star while the other remains in complete darkness. This state is called tidal locking. Tidal locking happens when a planet's rotation becomes synchronized with its orbit. The same side remains in constant daylight, warmed without rest. The opposite side remains in permanent night, frozen under a sky that never brightens. There is no sunrise, no sunset, only two hemispheres locked in opposing fates. On the day side, temperatures can rise to extreme levels. Rocks crack, atmospheres expand, surface materials may melt or vaporize. Radiation from the star falls without pause, shaping the landscape into scorched plains and glowing horizons. On the night side, the air can freeze solid. Temperatures may fall so low that gases turn into frost. Winds howl across the darkness, carrying chilled air toward the boundary between light and shadow. This boundary region is one of the most intriguing features of tidally locked planets. It is known as the terminator zone, the thin line separating eternal day from endless night. Here, temperatures may be mild enough for liquid water to exist. It is neither too hot nor too cold, but suspended between extremes. Some scientists consider the terminator zone a possible refuge where life might survive if all other conditions are right. The behavior of air and heat on tightly locked worlds is complex. Warm air from the day side rises and flows toward the night side, where it cools and sinks. This circulation creates intense winds that can shape weather patterns unlike anything on Earth. Some models suggest jet streams so fast they could circle the entire planet in a single day. Not all tidally locked planets are violent. If a planet's atmosphere is thick enough, it can redistribute heat, softening the temperature contrast between day and night. In these cases, the world may still experience permanent light and shadow, but without the extreme differences in climate. These planets teach astronomers how deeply a star influences the nature of its worlds. Orbit too closely, and rotation slows until time itself becomes lopsided. One half of the planet is locked into perpetual sunrise. The other remains in endless midnight. By studying tightly locked worlds, scientists better understand the delicate balance that gives Earth its cycle of day and night. Our rotation provides rhythm, temperature, stability, and a dynamic climate. Without it, our world would be unrecognizable. Each tidally locked planet discovered adds another example of how diverse and unusual planetary environments can be. Some worlds live in the glow of constant daylight, others dream in unbroken darkness, and between them lies a thin gray band where the conditions for life might flicker briefly in the soft twilight. As astronomers searched deeper into the galaxy, they found a class of planets unlike anything in our solar system. These worlds are called super-Earths. They are larger than Earth, but smaller than Neptune, sitting in a middle category that does not exist here at home. Their sizes range from 1.5 to 2 times the diameter of Earth, and their masses can be several times greater. At first glance, super-Earths seem promising. A rocky world with more land, more materials, and a thicker atmosphere might sound ideal for life. But their increased mass creates an environment that differs dramatically from Earth's. Strong gravity shapes nearly every part of these planets, from their landscapes to their air. Gravity on a super-Earth pulls downward with far more force than it does on Earth. A person standing on the surface would feel heavier, as if carrying several times their own weight. Walking would be slow. Jumping would be nearly impossible. Over time, such gravity would strain muscles, bones, and even internal organs. The atmosphere on a super-Earth also reflects this gravity. A stronger pull means gases are held tightly near the surface, forming a thicker and heavier blanket of air. This dense atmosphere traps heat, increases pressure, and alters the chemistry of the sky. The horizon may appear hazy or dim as light struggles to pass through the deep layers of gas. Mountains on these planets cannot grow tall. Under strong gravity, rock collapses easily. Landscapes become low and wide, shaped by the weight pressing down from above. Even oceans behave differently. Waves move slowly, and deep water sinks under intense pressure, forming thick, heavy currents. Weather on super-Earths can be powerful. Dense air allows storms to grow immense, with winds that push against the surface like flowing water. Clouds may hang low, suspended in thick layers. The atmosphere can create extreme greenhouse effects, raising temperatures far above Earth-like levels. Despite these challenges, super-Earths fascinate scientists because they show how flexible planetary formation can be. They demonstrate that being rocky is not enough to make a world familiar. The mass, gravity, and atmosphere work together to create conditions that may be stable but harsh. Studying these planets helps astronomers understand how delicate Earth's balance truly is. Our gravity is strong enough to keep an atmosphere, but gentle enough to support complex life. A little more or a little less would change everything. Super-Earths remind us that even slight differences in a planet's size can reshape the entire environment. They are stable, enduring, and intriguing, but they show that bigger does not mean better. It simply means different, shaped by the quiet and constant pull of gravity. Among the many kinds of worlds found across the galaxy, some of the most unsettling are the ones that travel alone. These are rogue planets, worlds that drift through space without a star to warm them. They do not orbit anything. They simply move through the darkness, guided only by their original momentum and the weak pull of distant gravity. Rogue planets are created in several ways. Some form normally around a star, but are later thrown out of their systems. This can happen when two giant planets interact, pushing one world outward with enough force to escape the star's gravity. Other rogue planets may have formed in isolation, born from collapsing clouds of gas that never gathered enough material to ignite into a star. Without a star, these planets receive almost no light or heat. Their surfaces can reach temperatures close to absolute zero, the coldest possible state. Any atmosphere they once had may freeze out and fall to the ground as frost. Oceans, if they existed, would become solid ice that never melts. Yet these worlds are not completely inert. Deep beneath their frozen crusts, heat from the planet's interior may still persist. Radioactive elements in the core release energy over billions of years. This internal warmth can create underground oceans or pockets of liquid water, shielded from the vacuum of space above. The motion of a rogue planet is silent and relentless. It travels through the galaxy like a dark stone skipping across a cosmic ocean. There is no sunrise or sunset, no seasons, no cycles. Time passes without rhythm. The sky remains black, except for distant stars that offer no warmth. Because rogue planets lack a star, they are extremely difficult to detect. They do not reflect sunlight. They do not block starlight. They reveal themselves only when their gravity briefly warps the light of a distant star, an effect called gravitational microlensing. This makes them some of the most mysterious objects in astronomy. Scientists believe there may be more rogue planets than planets bound to stars. Some estimates suggest billions of them drift through our galaxy. If true, this means the majority of worlds in the universe exist in isolation, never illuminated, never warmed, and never seen. Studying these planets teaches astronomers how fragile planetary systems can be. A small gravitational disturbance can eject a world entirely. A slight change in orbit can become permanent exile. Rogue planets remind us that stability is not guaranteed. Worlds can be created, shaped, and then cast out, left to wander in the dark. Their existence expands our understanding of what a planet can be and shows how many stories unfold in silence, far from the light of any star. As astronomers compare distant exoplanets with our own world, a quiet understanding began to form. Earth, which feels solid and unchanging beneath our feet, is supported by a balance far more delicate than most people realize. Studying other worlds helped reveal just how rare and intricate that balance truly is. Many exoplanets show us what happens when even a single environmental factor shifts too far. Some orbit stars that flare violently, releasing bursts of radiation strong enough to strip away an atmosphere. Others have atmospheres so thick that heat becomes trapped, turning the surface into a furnace. Still others orbit too far from their stars, where cold turns oceans into permanent ice. These worlds demonstrate how easily stability can collapse. A slight change in temperature, distance, or chemical composition can transform a planet into something unrecognizable. Earth's climate, which supports forests, oceans, and life, exists within a very narrow band of conditions. Move outside that band, and the environment changes entirely. When we observe planets with unstable skies or violent weather systems, we see reflections of what Earth could have become. A thicker atmosphere might have turned our planet into a world like Venus, overwhelmed by heat. A thinner atmosphere might have left us barren like Mars. A slightly dimmer sun or a slightly different orbit could have stalled the development of life. Continued exoplanet discoveries reinforce this message. Earth is not typical, it is fortunate. Our temperature, pressure, and atmospheric mixture are not guaranteed outcomes of planetary formation. They are the result of billions of years of gradual adjustments and rare coincidences. Even Earth's stability is temporary. Our climate shifts slowly. Oceans rise and fall. Continents drift. The sun brightens over time. These processes remind us that stability is not a permanent gift, but a moment within a much longer cosmic story. By studying the extremes found across exoplanets, scientists gain a clearer understanding of what makes Earth habitable. They learn how fragile the balance is between too hot and too cold, too thick and too thin, too active and too quiet. Exoplanets reveal not only the diversity of worlds in the universe, but also the extraordinary precision that allows Earth to sustain life. They remind us that our planet is not inevitable. It is exceptional, held together by conditions that align just right, for reasons still partly mysterious. In the silence of distant worlds, we see the truth about our own. Earth is strong enough to hold life and fragile enough to lose it. And that duality shapes every step we take as we look outward, searching for understanding among the stars. As scientists studied thousands of exoplanets, they noticed a pattern that explains much about the universe and our place in it. Liquid water, the most basic ingredient required for life as we understand it, is astonishingly difficult to maintain. It exists only when a planet achieves a near-perfect balance of temperature, pressure, and atmospheric composition. Water behaves differently depending on conditions. If a planet is too close to its star, water evaporates and becomes steam. If the planet is too far, water freezes into ice. Only within a narrow temperature range can water remain liquid. This narrow range is often referred to as the habitable zone, but even this term does not capture the full complexity. A planet may sit in the right region and still fail to keep liquid water. If the atmosphere is too thin, water will evaporate into space. If it is too thick, heat becomes trapped and oceans boil away. The exact mixture of gases matters. The pressure at the surface matters. The presence of clouds matters. Small differences can entirely reshape the fate of water. Venus once may have had oceans, but a runaway greenhouse effect evaporated them. Mars had rivers and lakes, but it lost most of its atmosphere and those waters vanished. These examples within our own solar system remind us how easily water can disappear. On many exoplanets, extreme conditions push water into unusual states. It can become supercritical fluid, behaving as both liquid and gas. It can become high-pressure ice, a form far denser than anything found on Earth. Some worlds are covered in global oceans that are hundreds of kilometers deep, where pressure turns the lower layers into exotic forms of ice. The rarity of stable, long-lasting liquid water teaches astronomers that Earth's oceans are not guaranteed outcomes of planetary evolution. They are products of specific timing and delicate balance. Earth formed at just the right distance from the Sun, with just the right atmosphere, and held onto its water for billions of years. Even slight changes in sunlight, volcanic activity, or atmospheric composition could have shifted Earth into a frozen or scorched state. Our oceans exist because countless variables aligned in our favor. Each exoplanet observed reinforces this lesson. Water is common in the universe, but liquid water is not. It requires a harmony of conditions that few worlds possess. By understanding how rare this state is, scientists gain deeper appreciation for the oceans that shape Earth's climate, support life, and define our landscape. Liquid water is a fragile achievement, one that marks our world as an exception among the many planets drifting through space. As astronomers compared the conditions of distant exoplanets with the environment on Earth, they realized that life does not simply appear wherever there is water or sunlight. Life requires a window of conditions so narrow that even small changes can close it completely. This window depends on temperature, chemistry, pressure, radiation, and time, all working together in a delicate partnership. Life as we know it needs molecules to move, react, and combine. These reactions occur only within specific temperature ranges. Too hot, and complex molecules break apart. Too cold, and they cannot move enough to interact. Many exoplanets fall into one extreme or the other, creating environments where chemistry struggles to begin. The atmosphere also plays a critical role. A planet must maintain enough pressure to keep liquids stable and allow gases to circulate. If pressure is too low, essential molecules escape into space. If it is too high, chemical reactions slow or stall under the weight. Even small differences in atmospheric composition can prevent life from taking root. Radiation from the host star influences this window as well. A stable star like the Sun provides steady energy, but many stars flare unpredictably. These bursts release harmful radiation that can sterilize a planet's surface or strip away its atmosphere. Some planets receive too much radiation. Others receive almost none, leaving their surfaces cold and inactive. Time may be the most important factor of all. Life requires billions of years of stability to grow complex. A planet that remains habitable for only a short period cannot support long-term evolution. Many exoplanets undergo rapid changes in climate or orbit, shrinking the window before life has the chance to begin. When astronomers observe these limitations across the galaxy, they gain a deeper understanding of Earth's rare opportunity. Our planet remained stable for billions of years. Temperatures stayed within a narrow band. Radiation stayed moderate. The atmosphere remained thick enough, but not too thick. Oceans endured without evaporating or freezing. This combination allowed simple molecules to form, then evolve into cells, then into organisms, and eventually into complex life. If any one factor had shifted too far, the process would have stopped long before reaching this point. The narrow window for life shows us that habitability is not just about having ingredients. It is about maintaining balance. The right conditions must last long enough for life to develop, adapt, and spread. Every exoplanet discovered outside this window reminds us how easily that balance can break. Every world within it, even briefly, shows how extraordinary Earth's story truly is. When scientists imagine life on distant exoplanets, they do not picture perfect copies of Earth. Instead, they consider how any civilization, if it exists, would have to adapt to the unique environment shaped by its star. A star is more than a source of light. It is the clock, the climate, and the foundation of every world that orbits it. Many exoplanets circle stars very different from our Sunday. Some orbit red dwarfs, small stars that glow dimly but remain active for trillions of years. These stars often release sudden flares that fill nearby space with radiation. A civilization living under such a star would need to build protection into its daily life, perhaps living underground or beneath thick atmospheres to escape constant bursts of energy. Other planets orbit stars much brighter and hotter than the Sunday. Their daylight is intense, with ultraviolet radiation strong enough to damage organic molecules. Any life or civilization there would need shielding, pigments, or structures capable of filtering harsh light. Architecture might evolve not for beauty, but for survival. Some exoplanets orbit so close to their stars that a year passes in just a few days. A civilization living in such a world would experience time differently. Seasons would vanish, days and years would merge. People might grow up in a sky where the star rises and sets constantly, or perhaps never moves at all if the planet is tightly locked. Even the color of the sunlight matters. A red star produces a dim, warm glow. A blue star floods the surface with brilliant, intense light. Plants, if they evolved, would not be green. They would adapt to the wavelengths available, creating landscapes colored by alien pigments. Gravity changes civilization as well. A world larger than Earth would shape bodies that are shorter, stronger, and more compact. A world with lighter gravity might allow tall structures or wider biological forms. Over generations, life adapts to the weight of the world beneath it. If a planet receives little light, technology would evolve to capture every photon. If a planet receives too much, tools would evolve to scatter or block it. Civilization becomes a mirror to the star that sustains it. These possibilities help astronomers understand that life elsewhere would not resemble life here. It would not build the same homes, follow the same rhythms, or see the same sky. It would grow in response to pressures and energies that shape its world moment by moment. By imagining how civilizations might adapt under different suns, scientists gain a deeper appreciation for Earth's gentle conditions. Our sun is stable. Our days follow a steady rhythm. Our radiation levels allow life to flourish on open ground. Every exoplanet we observe reminds us that a star is not just a distant light. It is the architect of possibility, deciding what life can become under its glow. As discoveries of exoplanets increased, scientists began to notice a quiet and sobering pattern. The universe offers countless worlds, but very few resemble Earth in the ways that matter most. Many planets imitate one or two familiar features, such as size or temperature, yet fail to match the deeper balance required to sustain life. This pattern reminded astronomers that the universe does not promise a second Earth. It only promises diversity, Some planets are the right size but orbit stars that flare with violent bursts of radiation. Others orbit in comfortable regions yet lack atmospheres that can hold heat or protect their surfaces. Some possess air so dense that oceans evaporate. Others have air so thin that water freezes. The ingredients for habitability appear often, but the recipe for a stable world is incredibly rare. Even planets that seem promising at first can reveal unexpected problems upon closer study. A world might sit in the habitable zone, but rotate slowly, creating extreme cycles of heat and cold. Another might have a surface shaped by constant volcanic activity, filling the air with gases that block sunlight. Small differences accumulate over time, turning hope into harsh reality. These discoveries highlight how delicate Earth's own balance is. Our planet maintains the right atmosphere, temperature, pressure, and water cycle, not by guarantee, but by history. Billions of years of steady conditions allowed life to begin and evolve. Without this stability, Earth would resemble countless other worlds that never reached that point. The idea of finding a second Earth once seemed simple. Search for a rocky planet in the right zone, and life might follow. But exoplanets taught scientists that habitability is not defined by one or two traits. It is defined by the long-term cooperation of dozens of conditions. Change any one of them, and the world shifts toward heat, cold, drought, storms, or chemical imbalance. This understanding does not diminish the excitement of discovery. Instead, it brings clarity. It shows that Earth is not ordinary. It is unusual, a product of rare alignment rather than cosmic abundance. And recognizing this rarity helps astronomers approach new worlds with realism instead of assumption. By studying exoplanets, scientists learn that the search for a second Earth is not a quest for a duplicate. It is a search for a world that found its own stable path, one that supports life through different combinations of conditions. Such a world may exist, but it will not be easy to find. This realization deepens our understanding of our place in the cosmos. Earth is not just our home. It is an unlikely success story shaped by time, chance, and fragile harmony. And as we look outward, we see not replacements, but reminders of how exceptional our own world truly is. As astronomers mapped more exoplanets across the galaxy, an unavoidable truth became clear. Even with advanced telescopes, precise instruments, and growing knowledge, the distances between stars place strict limits on how far we can explore. The universe is vast in a way that defies intuition, and this scale shapes every attempt to reach another world. The closest star system to Earth is Alpha Centauri, a little more than 4 light-years away. 1 light-year is the distance light travels in a year, moving at the fastest speed possible. Even at that unimaginable speed, the nearest stars remain far beyond our physical reach. With current spacecraft technology, a journey to Alpha Centauri would take tens of thousands of years. Most exoplanets are not 4 light-years away. They are hundreds, thousands, or tens of thousands of light-years from us. Their light reaches our telescopes after traveling through space for centuries. By the time we observe a world, we are looking into its past. Whatever we see may no longer exist in the same state. Engineers have imagined faster spacecraft, including designs that use powerful lasers or fusion-based engines. These concepts could shorten travel times dramatically, but even then, the distances remain overwhelming. A ship traveling at a significant fraction of the speed of light would still take decades or centuries to reach the closest promising planets. The energy required for such missions is immense. Keeping a spacecraft functioning for that long, protecting it from radiation, and guiding it across interstellar space are challenges far beyond anything humanity has attempted. Communication would also become difficult. Messages sent from a distant exoplanet would take years to reach Earth. These limits force astronomers to study exoplanets indirectly. They examine starlight that dims when a planet passes in front. They measure tiny movements in a star's position. They analyze the colors of light that filter through planetary atmospheres. Each method provides clues, but not complete pictures. The limits of exploration do not diminish our curiosity. Instead, they shape it. They teach us patience and humility. They remind us that understanding the universe requires careful observation rather than quick arrival. These boundaries also highlight the value of our position in the cosmos. Earth is the only world we can reach, study, and protect directly. Until technology changes dramatically, our exploration will remain a journey of light, not travel. In accepting these limits, scientists gain a clearer view of the future. The stars are reachable only through observation for now. And while this may seem restrictive, it also ensures that every discovery is meaningful, earned through precision and a deep respect for the scale of the universe. As the search for exoplanets expanded, scientists and philosophers began asking a question that reached beyond science. If we ever gained the ability to travel to another world, should we go? The idea of exploration is exciting, but touching another planet raises ethical concerns that become clearer as we learn more about how fragile and varied planetary environments can be. Every planet carries its own history. Some may be barren. Others may host simple chemical reactions that could eventually become life. A few might even have ecosystems already in progress. Introducing Earth-based organisms, tools, or pollution to such worlds could permanently alter their natural path. This risk is known as contamination. Even a small number of microbes from Earth could spread across a vulnerable environment. They might outcompete native organisms or disrupt chemical processes that would have shaped the planet's future. In a universe where life may be rare, the responsibility to avoid harm becomes significant. There is also the issue of biological safety for humans. A new world could contain unfamiliar chemicals or microorganisms. These substances might be harmless or harmful, but without understanding them fully, the risk cannot be measured. Approaching another planet without knowledge could put explorers and the homeworld at risk. Even uninhabited planets present dilemmas. Mining their resources or altering their surfaces could erase geological records that contain clues about planetary formation. Once disturbed, these ancient signatures cannot be restored. To address these concerns, scientists developed guidelines known as planetary protection. These guidelines aim to minimize contamination. They include sterilizing spacecraft, limiting where we land, and carefully planning missions. These rules protect both new worlds and Earth. As technology improves, the ethical questions become more urgent. Should we send probes to worlds that might host life? Should we attempt to land on planets with atmospheres similar to Earth's? Should we terraform barren worlds to make them more like our own? Each question lacks simple answers. The ethics of touching another world extend beyond science. They touch on responsibility, humility, and respect for the unknown. A planet is not just a destination. It is a unique combination of history, chemistry, and possibility. Altering it may erase something that has taken billions of years to form. By recognizing these ethical boundaries, scientists hope to approach exploration with care. The universe is vast, and many worlds remain untouched. How we choose to interact with them will shape not only our scientific legacy, but also our moral one. In the end, the question is not only whether we can reach another planet, it is whether we should, and under what conditions. This understanding encourages thoughtful exploration, guided by curiosity, but tempered by caution and respect. As the search for exoplanets expanded, scientists and philosophers began asking a question that reached beyond science. If we ever gained the ability to travel to another world, should we go? The idea of exploration is exciting, but touching another planet raises ethical concerns that become clearer as we learn more about how fragile and varied planetary environments can be. Every planet carries its own history. Some may be barren. Others may host simple chemical reactions that could eventually become life. A few might even have ecosystems already in progress. Introducing Earth-based organisms, tools, or pollution to such worlds could permanently alter their natural path. This risk is known as contamination. Even a small number of microbes from Earth could spread across a vulnerable environment. They might outcompete native organisms or disrupt chemical processes that would have shaped the planet's future. In a universe where life may be rare, the responsibility to avoid harm becomes significant. There is also the issue of biological safety for humans. A new world could contain unfamiliar chemicals or microorganisms. These substances might be harmless or harmful, but without understanding them fully, the risk cannot be measured. Approaching another planet without knowledge could put explorers and the homeworld at risk. Even uninhabited planets present dilemmas. Mining their resources or altering their surfaces could erase geological records that contain clues about planetary formation. Once disturbed, these ancient signatures cannot be restored. To address these concerns, scientists developed guidelines known as planetary protection. These guidelines aim to minimize contamination. They include sterilizing spacecraft, limiting where we land, and carefully planning missions. These rules protect both new worlds and Earth. As technology improves, the ethical questions become more urgent. Should we send probes to worlds that might host life? Should we attempt to land on planets with atmospheres similar to Earth's? Should we terraform barren worlds to make them more like our own? Each question lacks simple answers. The ethics of touching another world extend beyond science. They touch on responsibility, humility, and respect for the unknown. A planet is not just a destination. It is a unique combination of history, chemistry, and possibility. Altering it may erase something that has taken billions of years to form. By recognizing these ethical boundaries, scientists hope to approach exploration with care. The universe is vast, and many worlds remain untouched. How we choose to interact with them will shape not only our scientific legacy, but also our moral one. In the end, the question is not only whether we can reach another planet, it is whether we should, and under what conditions. This understanding encourages thoughtful exploration, guided by curiosity, but tempered by caution and respect. As astronomers searched the galaxy for signs of life, they expected to learn about distant planets. Instead, they found themselves learning about humanity. The search for life beyond Earth became a mirror, reflecting our hopes, fears, and understanding of what it means to exist in a vast universe. Every exoplanet discovered carries a question. Could life form here? Could it survive? Could it evolve? These questions push scientists to examine the conditions that allowed life to grow on Earth. They highlight the rare combination of factors that shaped our oceans, atmosphere, and climate. When we study barren worlds, we see versions of Earth that might have been a planet too cold, where oceans freeze, a planet too hot, where the atmosphere collapses, a planet too dry, too stormy, or too unstable. These comparisons help us understand that life on Earth is not guaranteed. It is the result of billions of years of stability. The search also reveals our assumptions. We often imagine life in Earth-like forms, using water, breathing air, needing sunlight. But as we observe more exoplanets, we realize that life might not follow our expectations. It could use different chemicals, different energy sources, or live in environments that seem impossible to us. This realization broadens our thinking. It pushes us to consider life not as a single pattern, but as a spectrum of possibilities. It reminds us that our perspective is limited by our experience. At the same time, the search highlights human curiosity. We look for life because we want to know whether we are alone. We want connection. We want to understand our place in the cosmos. Each discovery brings a mixture of excitement and introspection. The more we search, the more we appreciate our own planet. Earth is not only a home, it is a rare world where life thrives. Its air is balanced, its temperature is stable, its water is liquid. These features seem ordinary because we experience them every day, but exoplanets show that they are extraordinary. Even if we never find another living world, the search itself has value. It teaches us to care for the world we have. It reminds us that life is precious, fragile, and our longing to understand the universe all become part of the journey. The search for life among the stars is not only a scientific quest, it is a human one, revealing who we are as much as what might exist beyond us. As astronomers discovered more exoplanets, they began to notice a pattern woven quietly through the data. Every new world offered a possibility, yet carried a warning. The universe seemed to present both invitations and reminders, showing us what is achievable and what can be lost. Some exoplanets reveal possibilities. They show climates that might allow liquid water, atmospheres that could support chemistry, or orbits that offer long periods of stability. These features spark curiosity. They encourage scientists to imagine what life might look like under a different sky. But other exoplanets show warnings. They display climates ruined by runaway heat, surfaces destroyed by tidal forces, or atmospheres stripped away by harsh radiation. These worlds reveal how fragile planetary environments can be. Small changes in temperature or pressure can lead to dramatic transformations. Hot Jupiters warn us about unstable orbits. Their closeness to their stars suggests that some planets migrate inward over time, moving into extreme heat. Frozen worlds warn us about losing atmospheric pressure. A thin atmosphere cannot hold warmth, and oceans turn to ice. Some planets swing wildly between conditions, reminding us that stability requires balance. These observations help scientists understand the pathways a planet can take. A world can thrive for millions of years, then slowly drift into uninhabitable conditions. Others never have the chance to begin. Exoplanets teach us that habitability is not guaranteed. It is maintained through long periods of calm and cooperation among natural forces. At the same time, these worlds expand our imagination. They show us volcanic planets, ocean planets, frozen giants, and scorched spheres. Each one pushes the boundaries of what we consider possible. They teach us that nature experiments endlessly, forming planets in combinations we would never predict. The blend of possibility and warning helps refine our understanding of Earth. Our world sits within a narrow zone of comfort, supported by the right atmosphere, orbit, and temperature. Exoplanets show us the alternatives. They help us see how easily that balance can shift. This duality shapes the future of exploration. Each promising world suggests that life might arise elsewhere. Each harsh world reminds us to care for the environment we have. Together, they form a cosmic message. The universe is creative, but it is also unforgiving. As we continue to study these distant planets, we learn to read the lessons they offer. Some inspire hope, others inspire caution. All of them deepen our understanding of what it means for a world to be alive, stable, and capable of enduring the passage of cosmic time. As scientists look deeper into the growing catalog of exoplanets, they encountered a quiet realization that shaped the meaning of their discoveries. The feeling of regret, hinted in the idea of finding other worlds, did not come from fear or disappointment. It came from understanding. The truth revealed by distant planets was not that the universe is hostile, but that Earth is rare. Many exoplanets mirror certain aspects of our world. Some have the right size. Some orbit in gentle zones. Some hold thick atmospheres or deep oceans. Yet none match the full harmony that makes Earth what it is. Each planet carries one part of the equation, sometimes two, but never the complete balance. A world may be warm enough for water, but lack the pressure to keep it stable. Another may have the right pressure, but orbit a star that flares unpredictably. A third may have oceans, but no land, or land, but no air. The combinations vary endlessly, but the outcome is the same. Earth remains the exception. This understanding leads to a subtle kind of regret. Not regret in the emotional sense, but recognition that we may never find a world that mirrors our own. It is not the universe withholding something from us. It is the universe reminding us that what we have is extraordinary. Exoplanets show us the many ways a planet can exist. They reveal volcanic giants, frozen deserts, boiling oceans, and wandering worlds without stars. They teach us about atmospheric chemistry, orbital mechanics, and the fragility of climate. But in doing so, they also teach us about Earth's uniqueness. Our air is thin enough to breathe and thick enough to protect. Our oceans remain liquid. Our star is steady. Our temperature is stable across billions of years. These conditions are not guaranteed. They are achievements of cosmic chance and long-term balance. The silent truth behind our discoveries is that Earth's story does not repeat easily. The regret we feel is really gratitude in disguise. It is the awareness that our planet is precious precisely because it is fragile. Studying distant worlds helps us understand our own world more deeply. It encourages us to protect what we have, to appreciate the balance that allows life to thrive, and to recognize that our home is not one of many. It is one of a kind. In the quiet space between stars, exoplanets offer lessons rather than replacements. They remind us that the search for other worlds is ultimately a search for perspective, and that the truth we uncover reflects the rarity of our own existence in the vastness of the cosmos.